AGN, and Dan has so beautifully covered everything related to accretion disks and coronae that are visible in radio quiet AGN. I will really focus on the jetted and the radio loud AGN in this talk. So just to refresh what kind of AGN they are, and back to those that Stan had covered. They were mostly the Seyferts and the radio quiet quasars. Talked about Seyfert 1 and Seyfert 2 galaxies. Among those hosted by elliptical galaxies, then there are the more powerful quasars, those that don't have a significant jet radio quiet. And I will focus more on those that actually do have strong jets, those radio louds. Then one can distinguish between the prominence of the radio spectrum and the hardness of the radio spectrum. There's steep spectrum radio quasars. For myself, more interesting, those with flat spectrum with really dominant jet emission throughout the electromagnetic spectrum. There are, for once, radio galaxies, distinguished between FR1 and FR2 radio galaxies. So here the radio emission essentially dominated by synchrotron emission from electrons accelerated at the termination of these relativistic jets. And depending on the profile of the intensity distribution, they're called Fanarov-Rayleigh type 1 or Fanarov-Rayleigh type 2 galaxies. Type 1 means that the intensity is maximum in the beginning, in the center, and the jets are rapidly decelerated, dissipate their energy right close to the core, and then the intensity drops off. Whereas FR2 radio galaxies are characterized by jets remaining straight and collimated for many, often hundreds of kiloparsecs out, much larger than the size of the galaxy, and then are dissipated in these radio lobes, hundreds of kiloparsecs away from the core. And then, on the other hand, there are blazars, and those are the sources that I will really focus on. I think they're probably the most interesting kinds of AGN. And I will introduce exactly what they are, so we don't need to talk more about them now. Now, about these jets of AGN, they are in many cases really seen throughout the electromagnetic spectrum, from radio through optical. Now, with Chandra and other high-resolution instruments, we can even resolve some jets also in X-rays. It's only in the gamma rays that, well, the spatial resolution is so poor that there's really only one extragalactic source, Centaurus A, that has been marginally resolved in gamma rays. Otherwise, in gamma rays, and is still not quite able. Maybe one anecdote here. This was one of the very first images released by Chandra back in 1999. And the funny thing here is, this is a bright quasar at a pretty significant distance, about 6 billion light years away. And when people pointed at that, they actually wanted to do that to check the point spread function, because a bright quasar at that distance, that must be a point source. But what they actually saw was this, so the first actual X-ray resolved jet. Now, with these jets, what we see really depends on what angle we're looking at. We've talked about radio galaxies a little bit. In radio galaxies, we're looking at these jets just from the side. Quite often, we don't actually see the jets themselves, because material moves out here with almost the speed of light. Everything is boosted along the direction of the jet, which is pointing away from us. So we don't really see much of the jet. We only see where the jet kinetic energy is finally dissipated in these radio lobes. But there's a few occasionally where we actually look right down the jet. And those are the sources we call blazars, flat spectrum radio quasars, or BL-like objects, the two subclasses of blazars. And here we often only see one jet because, and I will talk much more about that in a little bit, because the emission is strongly Doppler boosted in the direction of motion of the jet. So we only see the one strongly enhanced that is pointing towards us. There's the same jet going in the opposite direction, but there the light is boosted away from us, so we don't actually see it. So what are these blazars? Essentially a contraction, the word of BL-like objects and quasars. And if in any Windows program you try to type blazars, it will always auto-correct it to blazers. So I always have to correct it. So they are seen throughout the electromagnetic spectrum. Actually, the most numerous source of gamma rays outside of our own Milky Way. They are dominated by these relativistic jets. I will talk much more about superluminal motion that we see in individual components, the jets moving along these jets. They're strongly polarized, at least at low energies in radio and optical. So if we plot their spectral energy distributions, so from frequencies from radio all the way through infrared optical X-rays and gamma rays, you see that this is very broad, non-thermal emission dominated throughout the entire electromagnetic spectrum by emission from the jet, most likely. There's a low energy emission component, which is pretty well established, but that is synchrotron emission from relativistic electrons in those jets. And then there's a second component at X-rays and gamma rays, where there's two fundamentally different possibilities of what might make the X-ray and gamma ray emission. I will discuss those in a bit. Now, blazars are classified essentially depending on where this low frequency component, the synchrotron component, is peaking. There's a class of low synchrotron peaked quasars, that low synchrotron peaked blazars. All flat spectrum radio quasars belong to this class. There's no known flat spectrum radio quasar that has a synchrotron peak much beyond, say, the infrared. So, but there's also a class of low frequency peak BL objects that belong to these. So defined by the synchrotron component peaking below about 10 to the 14 hertz. That means peaking below the optical range. And if you compare the intensity of the synchrotron and the high energy component, in these sources, most often the gamma rays actually dominate the total output in radiation. And if we look here at the X-ray band in these sources usually probes the low energy end of this high energy component. Then in the other extreme, we have high synchrotron peaked blazars, where the synchrotron emission actually peaks in the X-rays, in some cases even beyond the hard X-rays. And the gamma rays often even peak beyond the Fermi-Lat band here. So this butterfly here is a Fermi-Lat gamma ray spectrum, and this is a Cherenkov telescope spectrum at TeV energies. So here the synchrotron component peaks beyond 10 to the 15 hertz. So that means at least in the ultraviolet, often in the X-rays and beyond. And quite often, in fact, the power output in radiation is dominated by the synchrotron emission, and the gamma ray emission often subdominant. And then there's intermediate sources where the synchrotron component peaks between 10 to the 14, 10 to the 15 hertz. Most of these are also, all of these are also BLAC objects. And here, interestingly, I'll say a bit more about that. The X-ray band actually covers kind of the transition between the synchrotron and the high energy component. Now, as I said, these things are highly variable across the entire electromagnetic spectrum. You see here the TeV gamma rays, see here X-rays, photon index, optical bands. And quite often, what's interesting, you don't see just the emission in all wavelength bands going up and down in tandem. You often see these flares and variability features not really correlated between different energy bands. This is actually one famous example where you see here the TeV gamma ray flux shooting up in a big flare, whereas the other bands here, the X-rays and optical, don't do anything. So it's only the gamma rays shooting up and the synchrotron component not really doing anything. It's actually still a big mystery what is actually causing this kind of, as Stefan calls, orphan flares. Another example here of variability where you actually see, for example, the gamma rays and optical quite well correlated. So that's what makes these quite confusing. Sometimes things are well correlated between bands, but sometimes also not. Another example here from a campaign that I had led some time ago. So this variability, the variability we've seen here, if you look at the times here, this is in days. So here variability you see is on time scales of maybe a couple of days or a week or so. But the variability can be much faster than that. You see here, this is 1 day here. You see variability definitely faster than 1 day. And there's extreme cases, especially at very high energy gamma rays, where variability has been seen. Now here we're talking about minutes. So here's variability on time scales of really just down to a couple of minutes. So these can be extremely rapidly variable. And then keep in mind, these things outshine their entire galaxy by factors of thousands and more. So there's extremely bright and at the same time, extremely rapidly variable. And it's not only the flux that's variable. So we see here multi-wavelength light curves again over a couple of months time. But also here you see the polarization degree and the polarization angle. And you see that not only the flux, but also the polarization degree and angle are rapidly variable. So the polarization itself is a big clue that we're dealing with synchrotron radiation. As I said, this is pretty well established that in radio, infrared, optical, at least, we're dominated by synchrotron emission. So synchrotron radiation is polarized. I'm pretty sure you have all seen that. The maximum degree of polarization, if you have a perfectly ordered magnetic field, is related to the electron spectral index P by this expression. And so for indices between 2 and 3, that means you could, in principle, be polarized up to 65, 75%. What is actually seen, polarization degree, is at maximum something like 30%. This is already quite extreme. In most cases, we see polarization degrees of 5, 10, 15% or so, which tells you, as you would expect, that the magnetic field is not perfectly ordered, but you have some kind of curved, turbulent magnetic fields. You see a rather extended region of the jet where you don't have the same magnetic field orientation everywhere. And so, again, both the degree of polarization and polarization angles are variable. And sometimes, again, another mystery that's not well explained is that you see this polarization angle swinging around by 180 degrees or more. At the same time, that's the gamma rays and also optical fluxes are flaring up. What is actually causing that is still quite a bit of a mystery. There's quite a number of models out there what could cause this. Now, I've said that most likely all of this broadband emission is dominated by the beamed emission from the jet. There's a very fundamental argument that tells us directly that the emission must be relativistically beamed. It cannot be a source just sitting there radiating isotropically in all directions. That's mainly based on this combination of this fast variability of much less than 1 day, and we've seen it's even down to minutes, at the same time as the luminosity that one infers if one assumes that the radiation goes out equally in all directions, then the luminosity would actually correspond in many extreme cases over 10 to the 48 ergs per second. So if we just assume that this is just a static source that's not moving anywhere, the causality argument gives us a limit on the size. But the simple argument that if you have a certain size, something varies rapidly, what you get from the back of the source takes some time, light crossing time through the source, longer to reach us than the front of the source. So no matter how fast anything is varying, this light travel time effect will always smear out the variability over at least the light crossing time of your region. So that means if you see a certain variation on a certain time scale, T variability, then the source must be smaller than C times this variability time scale. So if we talk about a day time scale, that means the source, if it's stationary, must be smaller than a few times 10 to the 15 centimeters. Now, no matter what is actually causing this, the mass that is responsible for powering this emission must be smaller, so that this size is smaller than the Schwarzschild radius. So if you have a very massive source and you have a radiation source that would be smaller than that, than the Schwarzschild radius, then no radiation would actually get out. So that means the mass involved must be smaller than a limit just given by this being the Schwarzschild radius. And then if we have a certain mass powering this, Dan has introduced the concept of the Eddington limit. So the luminosity must again be less than the Eddington limit. And the mass directly gives you that Eddington limit. So that means the luminosity for a given variability timescale that determines the size, that determines the mass, gives you a limit on this on the luminosity that you can get up. So no matter what actually does that, even if it's not powered by accretion or so, if the luminosity is larger, the source would just essentially blow itself apart by its radiation pressure. So the argument still holds no matter what actually powers this. And this was realized actually very early on already at the time of E-grid in the 1990s. This is from a review paper by my PhD advisor from 1996. So already back then in the very early times of gamma ray astronomy, it was clear that there's a couple of sources here where the luminosity, so there's plotted here the luminosity and here the variability timescale. And we have to have, this is the limit that corresponds to this Elliott-Shapiro relation. And anything that wouldn't violate the stationary constraint must be in the white area here. But there are some here where the luminosity is too large or the variability timescale too fast to be consistent with this. So very early on in the 90s already, the Compton Gamma Ray Observatory, it was clear that the emission must be relativistically beamed by something moving along the jet. So what does this beaming actually look like? If we assume we have a source that is moving along the jet in the source's frame itself, everything is going out isotropically in all directions, with frequency, call that nu prime, intensity I prime, and variability time T bar prime. Then if we look at this in a stationary frame, when the source is moving at a large Lorentz factor, or that capital gamma, then everything is determined by this Doppler boosting factor, 1 over gamma, 1 minus beta cosine of our viewing angle with respect to the motion here. Then the intensity is intrinsically boosted. Also, flux that we observe is boosted by 3 factors of this Doppler factor. At the same time, also the frequencies are boosted. So that means if we have a power law of emission, we boost in frequency and 3 powers up in intensity. So then the observed flux, if we compare the same frequencies, are Doppler factor to the power of 3 plus the spectral index. And at the same time, so we're winning with respect to this Elliott-Shapiro relation, because now the intensity is actually much less than what we would infer without beaming. And also the variability timescale is shortened for us as we observe it. So if we see, say, a day variability timescale, this Doppler factor is 10, then in the source frame itself, the variability is actually only on 10 days, not just 1 day. So that helps us in both directions. So the variability is actually not as extreme intrinsically as we infer, and the luminosity is much less because we see it very strongly boosted. And so this is what I referred to. If we have an intrinsic spectrum here with a power law near to the minus alpha, then we boost all emission by 1 factor in frequency, 3 factors in intensity. And so that means if we compare the same frequencies in both frames, then we get this boosting by delta to the 3 plus alpha. Or in a nu if nu representation, as we usually plot SEDs, that means that we end up boosting the nu of nu flux or the inferred luminosity by 4 factors of delta. So if we now don't take into account that it's not isotropic anymore, if we simply take this flux and infer a luminosity just by 4 pi distance squared, then the inferred luminosity is actually a factor of 4 Doppler factors larger than the intrinsic one. So that means if typically this Doppler factor is something of the order 10, then we actually see it 10,000 times brighter than it really is intrinsically. And this, of course, is the reason why these are actually quite frequent, even though it requires a very rare chance coincidence that this jet is pointing right at us, but because they are so bright, we can see them out to very large distances. Now, I mentioned superluminal motion already briefly. This is a phenomenon that has been seen in very high resolution radio observations. There's been intense programs, in particular this Mojave project that is using the VLBA in, in the US, monitoring with high angular resolution these jet structures of blazars over many, many years. You can see the years ticking by here. And one sees individual components of these jets moving along the jets. By the way, anybody know what's the more common name of this guy? It's a very famous blazar, actually. That's 3C279. And if one now, well, if we know the redshift of the source, we know the distance. So if we see something in angular velocity moving across the sky, we can convert that to just linear velocity. And if one does that, one often finds 5, 10, 20 times the speed of light. So does that mean relativity is wrong? Luckily, no. But this tells us that we are actually looking at this jet at a very small angle. And the stuff moving along the jet that is radiating is moving with almost the speed of light. As a consequence, whatever light or radio waves the source has emitted is only a tiny little bit ahead of the source itself. And so everything that is emitted, say, over a year, is actually arriving bunched up on a much shorter time scale. So we see this arriving at our location in much shorter succession than it really has been emitted, just because the light is only a tiny little bit ahead of the source that is just emitted it. You can easily figure out the math of what we actually get for this superluminal motion. So if the stuff moves along the jet here at a small angle with respect to our line of sight, angle is theta, then the time difference between the source being here and time being here is once the actual time difference, well, minus whatever the light from here takes less to reach us than here. That is this projection V delta t cosine theta over the speed of light. So V over speed of light is our beta times cosine theta times delta t. So the actual time interval that we see between receiving the light from here and the light from here is this factor 1 minus beta cosine theta less than the actually elapsed time. And so that means the apparent velocity with which we see this component move across the sky is now the projection here, V times sine theta, over this contraction factor here, 1 minus beta cosine theta. And it's an easy homework to just take the derivative with respect to theta here to figure out that for beta equals cosine theta, this becomes maximum. And if you put that in here, then well, beta equals cosine theta, then this is 1 minus beta squared. So 1 over 1 minus beta squared is a gamma squared. And sine theta is square root 1 minus cosine square theta, but cosine square theta is beta squared. So this is 1 over gamma. So if you figure this out, then the maximum relative velocity, apparent superluminal speed, is actually the Lorentz factor times the speed of light. And so that means if we see an up to 30, 40 times speed of light, that means that at least in some blazars, the Lorentz factor of stuff moving along the jet must be of order 10 and more. So we're really dealing with stuff moving along the jet with essentially the speed of light. And that gives us this strong Doppler boosting that helps us see these sources out to very large distances. Now, let me talk a little bit more about the physical models for this broadband emission and the variability. A good theorist, of course, if you ask a theorist to build a model of a cow, we start out assuming it's spherical. And for a cow, obviously, that's a good approximation. But for something moving along the jet with relativistic speeds, interacting with stuff, that's obviously a very rough approximation. But surprisingly, these spherical cow models, in many cases, for many aspects, do a very good job actually in explaining many of the features that we see in laser emission. So in a class of models that we call leptonic models, it's only electrons and maybe positrons that do all the radiating. Most likely, there's also protons in there, but they're not relativistic, they're not accelerated to high energies that they contribute to the radiation. So we just have some kind of acceleration mechanisms. A week ago, I talked about all the possibilities of what could accelerate the particles. We don't really know what it actually is. But for the purpose of these models, it's often good enough to just assume that one of these mechanisms works. It accelerates particles into a non-thermal, say, power law distribution. Then this will evolve, will cool, particles will escape. So you have some more complicated spectrum of electrons. And then, as we said, the low frequency component in the SED is from synchrotron radiation of these electrons. And in the leptonic models, it's the high energy component is produced by Compton scattering. So you have relativistic electrons, upscattering low energy photons to high energies to X-rays and gamma rays. And there's quite a number of possible photon fields that can be upscattered. For example, the synchrotron radiation itself, or it can be external photons from the accretion disk, or all these components that Dan has nicely introduced. So there's emission lines here that can enter the jet and be upscattered. And there's this dust torus that produces infrared radiation that can be upscattered. So there's plenty of possibilities of what could be upscattered there. Now, there's an alternative that protons actually are accelerated to very high energies. And these kinds of models are getting more and more popular these days because, as I'll briefly mention, blazars seem to be more and more established, at least one of the possible sources of high energy neutrinos that have been seen by IceCube. So in this case, we then have both electrons and protons accelerated to ultra-relativistic energies. Still, the low energy emission is still synchrotron radiation from these primary electrons. But now the physics of this high energy component becomes quite a bit more complicated. So for once, if protons are highly enough relativistic, they can also radiate synchrotrons, so there can be proton synchrotron emission. But also these protons can interact with target photon fields like the synchrotron photon field or these external photon fields. And then the gamma interactions can produce neutral pions that decay into two very high energy gamma rays, or they can produce charged pions, and then charged pions produce muons. Muons decay to positrons and neutrinos. So in each one of these interactions, if there's a charged pion produced, we produce a total of 3 neutrinos, in fact. And that's what makes them so interesting as to explain the possible neutrino emission from blazars that has been seen by IceCube. And it would be a complete other 1-hour talk to talk about neutrinos and neutrino production in blazars. But the picture becomes more and more clear that blazars at least make some fraction of the neutrinos that IceCube has been seen. And also important, the gamma rays that are produced here by the pi0 decay and also by synchrotron radiation from these secondary particles here, they actually come out not here in this gamma ray bump, but way beyond at PeV and even higher energies. The problem there is that there's so many low energy photons, ultra high energy photons and low energy photons annihilate each other, make electron positron pairs. And then these pairs can radiate again, make more high energy gamma rays, that get absorbed again. So it trickles down to lower and lower energies. So whatever is produced way up here by these processes actually cascades down and comes out in a relatively flat spectrum below the frequency where everything becomes optically thick to gamma-gamma absorption. So the radiation that we actually get out of these processes finally comes out in these electromagnetic cascades that are produced by repeated gamma-gamma absorption, synchrotron radiation, more absorption, and so on. All right, so how can we constrain now all these models? Obviously, there's a lot of free parameters that in many cases we don't really know well what they are. So if we just take the very simplest model with only synchrotron radiation and Compton scattering of the synchrotron radiations, we call those synchrotron self-Compton models. They are already, that's the simplest model you can have. Just and even here you have what's the radius of the emission region that we don't really know, the Lorentz factor, the observing angle that gives us the Doppler boosting, the power that is going into these relativistic electrons, the characteristics of the accelerated electron spectrum, the magnetic field, something that defines the escape of particles from the region. So even in this very simplest model, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters that somehow we need to figure out what they are to explain this emission. So let's look a little bit at observables. What can we see and how can we try to pin down any of these parameters? So one I've already mentioned with the Alliot-Shapiro relation is, of course, the variability timescale. So if we see some kind of variability on a certain timescale, then now we know that everything is boosted. So the size is not only determined by the variability timescale, but also we see the variability smaller by a factor delta. And of course, the cosmological redshift will stretch times, so that works against us in a sense. But if delta is large, that actually allows for a larger region because we see the time contracted. So if we see variability on the hours that we often see in many of these blazars, that still pins it down to sizes of, say, 10 to the 15 centimeters if we have a Doppler factor of 10. Right? Now, another thing comes from variability. What one quite often sees is, as I said, you don't see everything going up and down in tandem in a correlated way. Quite often one sees, say, as you see here, high energy electrons being accelerated and injected first. And then you see this electron spectrum cooling down. So you see often first the hard spectrum, the high energy is going up first, and then it becomes soft as the flux goes down. And one can actually measure this directly. So in the cases in particular where the synchrotron actually then peaks here somewhere in the X-ray regime. And this has in fact been seen. This is what's plotted here. This is here the flux on the x-axis versus the spectral hardness. The higher up, the harder the spectrum is. And this has actually been seen already very early on in the 90s. I think this was from ASCA. So you see here how the source evolves in this plane of spectral hardness versus flux. You see that's the flux during this flare first doesn't really go up, but the spectrum gets hard. Then the flux goes up as the spectrum is hard. And then the flux goes down as the spectrum softens. So it's something that's called spectral hysteresis that is sometimes seen. And that is, I know X-ray astronomers often don't really like blazars because they're boring, it's just power laws. But you can see that one can learn a lot from these power laws, especially if they're so time variable, that they're still very interesting. Now, this translates directly also in time lags between the hard and soft gamma rays. Because the hard gamma ray, this is soft X-ray, sorry. The hard X-rays come first as the spectrum hardens, and then the flux goes up also at lower frequencies as the flux then later goes down. So this directly relates to a time lag between hard and soft X-rays. So here is, as a function of energy, the time lag that has been inferred from this feature with respect to hard X-ray reference frequency. And you see a very clear trend. The larger the frequency difference, the larger the time lag is. And this actually gives us a very good handle to determine the magnetic field if we actually deal with synchrotron radiation. So if this time lag really is the difference in electron cooling timescales between high energy electrons and lower energy electrons radiating at hard and soft X-rays, then, well, I'm sure you've all seen that the energy loss rate due to synchrotron radiation is something that's proportional to UB. Do I have here? No, I thought I had. Oh, see, that should have been there first. So energy density of the magnetic field, that goes as B squared times the Lorentz factor of the electron squared. So that means the cooling time scale goes like 1 over gamma times the magnetic field squared. And now we can resolve the gamma by knowing how the synchrotron, the characteristic synchrotron frequency is related to magnetic field and the Lorentz factor. So you can solve this for gamma to plug it in here. And then you can relate the cooling timescale as a function of magnetic field and these two frequencies between which you measure that time lag. And this you can easily resolve then for B, for the magnetic field. So if you measure at two frequencies a time lag between them, with the assumption that that time lag is really a difference in cooling timescale, you can actually figure out what the magnetic field is, modulo Doppler factor and redshift. Redshift we know, Doppler factor we often have a good handle from this superluminal motion. So there's other things one can infer just from looking at the SED. If you have a low frequency component here, peaking at a characteristic synchrotron frequency, high energy component, if we're dealing with leptonic models, so let's call this C for Compton, peaking at a certain flux and frequency, then the first thing we can infer is the ratio of the fluxes in synchrotron and Compton is actually given by the ratio of the targets that are being processed or scattered. Because the cooling timescales or the energy loss rates for synchrotron goes like UB times gamma squared. For Compton, it's radiation energy density times gamma squared. So the ratio of these heights of these peaks is the ratio of the energy density in magnetic field and the magnetic the radiation field and the magnetic energy density. And if we have an estimate of the magnetic field, we can figure out what the density of the radiation field is, and that probably tells us what that radiation field might be. But then also, if we have an idea of what the magnetic field is, then of course the synchrotron frequency tells us what the characteristic electron energy must be that is radiating. So that gives us another clue on the electron distribution. And we can infer that also if we can actually model this with synchrotron and synchrotron self-Compton, if there's no other radiation field. So if it's this radiation field, Compton upscattered to make this peak, then the ratio between these frequencies is again from the basics of Compton scattering is just the peak Lorentz factor of the electron squared. So it gives us another handle of the characteristic electron energy in the emission region. Or alternatively, if this is from an external radiation field and we have an idea of what's the peak of the electron distribution is, then we can infer what the characteristic frequency of the target photon field is. So just from looking at the SED, one has quite a lot of clues what the underlying physical conditions must be. Then, of course, from synchrotron theory, if we have a power law of synchrotron radiation, say here in the optical UV, then that, of course, gives us directly the electron spectral index. You know, the synchrotron spectral index is p minus 1/2. Can easily resolve that for p. And then just from the flux levels, again, that tells us something about the power in the electrons, because that essentially gives us the normalization of these components, especially if we have an idea what the magnetic field is and what the characteristic electron energy is, then we know how many electrons we need in order to produce this flux. So that gives us the total energy content in the jet, essentially, and the power in the jet. All right, so now a little bit more, since we are here at an X-ray school, a little bit more about what we can learn specifically from observing blazars in X-rays. So just a few highlights. So one I've already mentioned, we see the spectrohysteresis, we see time lags. That gives us a very important handle, in particular on the magnetic field in these regions. Another important aspect where X-ray observations are very helpful is, I think the first time this has really been measured was here in the prototype BLAC object, the Lacerte by Marcello Ravasio et al. In 2002. So in intermediate synchrotron peaked blazars, like the Lacerte belongs to this class, one actually sees in the X-rays the transition between synchrotron and the high energy, say in the Compton. And that gives us a handle of where actually this high energy component is beginning to set on. And that gives us essentially the spectrum of the electrons at the lowest energies. This is the lowest energy electrons that still radiate something, because high energy electrons make the gamma rays. And this is important because, so even if we have these relatively hard spectra, the underlying electron spectra often still have a spectral index steeper than e⁻². And that means even though the high energy electrons give you most of the radiation that you actually see, the low energy electrons actually carry still most of the energy, because there's so many more of them. Even though they're not really relativistic, they're not carrying individually so much energy, but there's so many more. So if the spectrum is steeper than gamma⁻², most of the power is still in the low energy electrons. And those, you don't see them in the radio, because in the radio, this emission region is optically thick to synchrotron self-absorption. So you can't probe these low energy electrons with radio observations. But if you get a handle here on the onset of the high energy component at the lowest energies, that gives you a handle of these relatively low energy electrons. And that then finally gives you a good handle on the kinetic power in the jet, because most of the power actually is in those low energy electrons, not in the highest energy electrons. And one other aspect that I briefly touched upon already is maybe just to get back here. And the problem here is that, because in terms of measurements, we have gamma ray instruments that measure typically at over 100 MeV. And then there's this really bad gap in observations. There's some ideas of missions like COSI to fill this in here. But there's really this big gap between like Fermi-LAT, that this is of course still from Egret. So between the high energy gamma rays and what we can see in X-rays, there's a gap of at least 1-2 orders of magnitude in frequency that we just don't observe. So the only handle we get on these lower energy electrons is really coming from the X-rays, because there's nothing in between. And now, as I already mentioned, there's more and more evidence that blazars are responsible for at least some of the ice cube neutrinos. That means 100 TeV, PeV neutrinos. And that, of course, means that we must have protons in these jets that produce neutrinos by photopion production. And as I've already said, whatever photons are produced, whatever ultra high energy gamma rays are produced, isn't coming out directly. It's absorbed and cascading down and ultimately comes out here. This is the cascade component that is produced by the gamma rays produced along with this is the neutrino spectrum in terms of energy plotted here. So whatever photons are produced along with making these neutrinos comes out actually at lower energy gamma rays and X-rays. So a lot of people have been looking for coincidences between Fermi gamma ray flaring and neutrino emission. There are some of these coincidences. Those of you who followed the field, the very first, say, significant coincidence between TXS 0506 and an IceCube event in 2017. That was actually a gamma ray flaring event with a neutrino. But there's many other coincidences now where there's a blazar that's seen flaring actually in other wavelengths, but not in gamma rays, when there's a neutrino coming from a direction consistent with that blazar. There's more and more of these instances. And instead of looking for the gamma rays that are likely absorbed in the source, one should actually look at X-rays. Because in X-rays, soft gamma rays and X-rays, that's where this cascade emission is really coming out. So you do not necessarily expect a correlation here with gamma rays. And again, as I said, this would be another whole hour talk. Won't go in much more detail, but you should actually look for timing signatures of flares in X-rays at the time that a blazar is active in producing neutrinos. So that's again where X-ray observations would be crucial to test this coincidence and to test the presence of this cascade emission that must be associated with producing neutrinos. So maybe one other highlight from very recent developments, and that is polarization. I think in the whole school, I haven't heard much about polarization yet, but this is really a new frontier that is just starting out now. And that's based on the fact that Compton scattering, that probably produces the X-rays and gamma rays in many blazars, is also polarization dependent. This is here the cross-section for Compton scattering in the electron rest frame as a function of the energy of the photon that's scattered before and after scattering, the dimensionless photon energy here, photon energy over MEC squared. And now if we look at this cross-section here, so this is the energies, and this is the polarization vectors, the electric vectors of the polarized photons before and after scattering. Now, in the Thomson regime really means the scattering is elastic in the electron rest frame. So that means in the electron rest frame, the photon energy is much less than the electron rest mass energy, and the photon essentially just bounces off with the same energy. In the Thomson regime, that means epsilon is almost the same as epsilon prime. Now then we have 1 plus 1 minus 2, so this all cancels out. All that's left is the dot product of the electric vector before and after scattering. So now let's assume there's a photon polarized in this way that goes towards you. And let's say you want to scatter this upward. Then the new electric vector must be perpendicular to the direction of propagation. But that means the electric vectors are perpendicular to each other, so the dot product is 0. So this never happens. So if you have a photon polarized in this way, you will never scatter up or down. You will preferentially scatter in the plane perpendicular to the polarization, and you tend to preserve the degree of polarization. So a polarized photon will preferentially be scattered in the plane perpendicular, and you preserve the polarization. So that's just to illustrate that the Compton scattering process is polarization dependent. And this can be exploited in detectors as well. This was actually one of the ideas for the AstroSat CZT detector, that there's some scattering medium here, producing one Compton scattering, and then you have a ring of detectors around it, in a sense. So then if there's a polarized photon coming in, let's say this is a photon produced by a synchrotron of ultra high energy electrons, then if you look towards the sky, the magnetic field in the source goes like this. That means the photon would be polarized in this way. Then if the photon is polarized this way, the scattering preferentially stretches the photons out perpendicular to that direction. So that means you would see in your detector an anisotropy of the scattered photons that are being detected. And this anisotropy is just pronounced in the direction perpendicular to the polarization of the photon. This was actually from a simulation here. So the angular anisotropy that you would expect for detection of polarized X-rays in astrocytes. Now, the big new development, of course, is that in December of 2021, the first really dedicated Compton polarimeter, not Compton, X-ray polarimeter has been launched. It's called IXPE, the Imaging X-ray Polarimetry Explorer. This is actually based not on Compton scattering, but the photoelectric effect. The photoelectric effect, you get a very similar effect. That's the electron is kicked out of the atom in the detector, primarily in the direction of the polarization. So if a polarized photon comes in, the electrons will be kicked out preferentially in this direction. And this is being measured here in medium energy X-rays, 2 to 8 keV. And maybe just two highlights from this mission, because the first results are now being published from this. First is the prototypical high-frequency PLAC object, Makarian 501. This has been observed twice by IXPE. And here, in fact, polarization has been significantly detected of the order of about 10%. It depends a little bit on the exact analysis method, what the result is, but they're all more or less consistent with each other. So here there's about 10% polarization in the X-rays detected by IXPE. And interestingly, if we now compare the X-ray polarization, this is as a function of frequency now, with polarization at lower frequencies. So here optical, here's radio. You see that the X-rays are actually more highly polarized than the optical. This is something that has been predicted for a specific model of a shock, where you have a shock going through your jet, compressing the magnetic field right at the shock front. So you have a very nicely ordered magnetic field right at the shock. Where you accelerate particles, you have the highest energy particles that cool away quickly. So only directly at the shock, you have both a highly ordered magnetic field and the high energy particles that make synchrotron X-rays. So there you get a high degree of polarization. The lower energy synchrotron in the optical is produced by lower energy electrons that have time to cool and move out, and sees a larger region behind the shock where the magnetic field becomes more disordered again. So they see a less ordered magnetic field, and therefore you see a lower degree of polarization. So this has actually been theoretically predicted by Cervecchio et al. And others. And this is now really seen. Doesn't necessarily have to be shock, but it tells you that you have a very small localized region where energy is released to accelerate electrons, where you have an ordered magnetic field that makes you the X-rays, and lower energy electrons being spread out over a larger volume. Another result from IXPE, just to have two examples, is the prototypical BLAC object, BLACerte. It's also been observed twice. And in this case, so you see here, the plot is the polarization direction, and the distance from 0 would give you the polarization degree. You see 1, 2, 3 sigma contours, and the 2 and 3 sigma contours in both cases are consistent with 0, so there's no significant polarization detected. In particular, there is significant optical polarization seen that must be higher than what is seen in X-rays. So here we are probably seeing the low energy SSC component, synchrotron self-Compton component, whereas in the optical we see synchrotron. And again, this has been predicted. If this is leptonic emission, synchrotron self-Compton dominating the X-rays, you'd expect the polarization to be significantly less than the synchrotron polarization. Again, this probably indicates that we are dealing with leptonic dominated high energy emission. That's all I have. Maybe one little advertisement. I know some of you actually have this book. This came out in 2012. Most books on active galactic nuclei really don't care much about jets. They really talk about the things that Dan was talking about. So this is one of the very few dedicated textbooks on relativistic jets. One of the editors, but there's a lot of people that have contributed to this book, and I can recommend this. Thank you.
Questions?
Yes, thank you very much for that wonderful talk. Now, looking at the spectral energy distribution of blazars, I'm wondering whether there is no thermal component of the emission, because I think the lower part of the emission is due to synchrotron radiation. Then the energy component is due to synchrotron self-Compton. So I'm wondering if there is no thermal component.
Actually, in many blazars, we do still see thermal components. Let me see if I have any here. No, not really. But let me just look at this. So in many sources, there is both often an accretion disk component seen directly. There's few where it's actually quite prominent. That is thermal emission. In many blazars, one sees in the optical actually signatures of the host galaxy. That is thermal emission. In some, we even see little excess in the infrared from the dust torus. So yes, you're perfectly right. There are thermal components. In many blazars, the jet just outshines everything. But there's also many blazars where we actually see these thermal components.
Any other?
Thanks for the very nice talk. Can you maybe comment on whether there are, you can get like a thermal electron population within the shock?
Yes,
and can one observe like a special signature in the spectrum that can maybe indicate there are additional components in the electron spectrum?
Yes, there's one idea, and that would be another talk. But there is actually some sources where there is an excess here between the synchrotron and the Compton. That's called often the big blue bump. That could be from the accretion disk here, but there's also the idea that if you have a thermal distribution in the jet that moves along, then this still moves with a large Doppler factor, with the jet Doppler factor of 10 or 15, 20 along the jet. That can also take external radiation fields and upscatter it. That's something that's called the bulk Compton effect. So that can also give you some kind of soft X-ray or UV access here. And this is seen. It's not clear if it actually is from this bulk Compton, but this big blue bump or soft X-ray access is seen in a few sources. And interesting thing, actually, if you have thermal electrons, low energy electrons, that Compton scatter something in the rest frame of that emission region, that would actually induce polarization. So polarization, X-ray polarization would actually be the signature that you would expect if this big blue bump is from the bulk Compton process. Yeah.
Any other question? Okay, last. Oh.
Can you watch the jet evolve, or the bulk Lorentz factor of the jet evolve with time from your observations?
Yes, with the same observations as we had here for the these kind of observations tell you precisely that. So when one follows these here, the Lorentz factor does not always stay the same. We see it changing. We see directions changing here sometimes. So obviously, the jets aren't always straight. They're sometimes bent. And one can actually see both accelerations and decelerations of these the superluminal motions. So one does see it change over time.
Okay.
Thanks, Prof, for a very good talk. I don't know if I may have missed this, but
do you usually calculate lag numbers for these shock fronts, and what are the typical values you get?
That is very poorly constrained, in fact. But if these are really shocks, internal shocks, I mean, they must be relativistic and the Mach numbers must be very high. But I can't give you a specific number now.
Okay.
Hi, I was just wondering, is the neutrino X-ray correlation like a fingerprint for hadronic emission? Like if there's maybe like a flare in X-rays that corresponds with a flare in neutrinos, is that like a definite like,
Yes, from the
indication?
model, it must be related, right? If you
Okay.
produce neutrinos, then you also have ultra high energy photons produced in the same process. And if you're in a region that's efficient in producing neutrinos, that means you have enough target photons to actually make neutrinos to have pion interactions, then that's another thing. The likelihood for a gamma ray to be absorbed is about 300 times higher than for a proton to make a neutrino. So if you are efficient in making neutrinos, then you're even much more efficient in that same region to absorb the gamma rays and make the cascade. So it's a very definite prediction that if this is the photopion production makes the neutrinos, then you must have the cascades and you must have an X-ray access associated with it.
So does that completely eliminate the possibility of leptonic emission, or can there still be a combination of hadronic and leptonic emission?
No, in fact, essentially all models these days begin to converge to a picture where the gamma rays might actually be leptonically dominated, even if you have a subdominant contribution of protons that makes the neutrinos. And the argument actually being from the X-rays, because if the whole gamma ray spectrum is made by these hadronic processes, then it tends to be too flat a spectrum and actually to overshoot the X-rays. So that's why most models these days agree from most sources that the gamma rays, the broadband electromagnetic emission is likely leptonically dominated, and you have some subdominant hadronic component that makes the neutrinos, and a relatively low X-ray flux resulting from it.
Okay, thank you.
Any other last question before the load setting kicks in?
I was just wondering about the polarization in the Thomson regime. What would you expect in the Klein-Nishina regime for that?
In the Klein-Nishina regime, it's much less pronounced, because then you have these energy dependent terms that dominate. So it's washed out in the Klein-Nishina regime.
Can you maybe comment on what's the source of the variability in the behavior of blazars?
That is one of the very big questions. Right? So, probably ultimately originate, it must somewhere in instabilities or inhomogeneities in the accretion flow that ultimately powers the jet.